talk about intermolecular forces first. And intermolecular, inter means between, and molecular obviously means molecules, but we can be talking about with intermolecular forces any separate particles. They could be molecules, they could be atoms, but if you have, let's say, a negative charge over here and a positive charge over here, we all know that negative charges and positive charges attract each other, and so there'll be this electrostatic attraction. That is what we mean by electrostatic. It's the attraction between negative and positive charges. And that's going to make these two particles, if they have this positive and negative attraction, it makes them sticky. And that's just one way to think about it. They want to kind of stick together. And if they stick together, they will form, strongly enough, they'll form solids. You have to really slow them down, take a lot of energy out to get them to form solids. If we put energy in and we can break those intermolecular forces so that they make and break them, we can turn them into a liquid. And the stronger these intermolecular forces, the higher the temperature that we need to melt something will be, the higher the temperature that we'll need to vaporize or boil a substance. So electrostatic forces are the forces between molecules, and it's how sticky molecules are of different substances. So what forces are responsible for condensed phases of matter? Condensed phases of matter are solids and liquids. So that's what we're talking about when we talk about condensed phases of matter, solids and liquids. Gases are not condensed phases of matter. I'm going to show you a simulation of water turning into ice. So this is actually the shape of a water molecule. If you've taken Chem 1, which you should have, you know that is an angular shape, that it's a very polar molecule with a partial negative charge up here on the oxygen end of the molecule and a partial positive charge on each of these hydrogens. And so when water molecules are in the liquid phase, they can move around each other, making and breaking those intermolecular forces that we call hydrogen bonding. And we're going to talk about hydrogen bonds in detail in a little bit. But when I take the energy out of the system by lowering the temperature, what they will do is they will line up and they will freeze in place. Now, they never stop moving, they vibrate. There's always residual energy in those water molecules. And what I'm going to show you now is a simulation of water turning into ice. We're going to freeze liquid water and we're going to turn it into ice. I'm going to turn this lamp off, which is really harsh. Here we go. So you've got the liquid water. We are taking the energy out. The temperature is constant while this phase change is taking place. The energy is coming out of the liquid water, and you can see it freezing. It's actually less closely packed together in this very organized form, which we call ice. Let's take another look at that. So you can see that the volume of space that the solid water, the ice, takes up is greater than it is as a liquid. They're actually more closely packed as a liquid. Water is one of the few substances that does that. That makes solid water, ice, less dense than liquid water. And so what we have here, when we take that energy out, is we have very sticky molecules of water which are adhering to each other through the hydrogen bonds. Here in the liquid phase, they're vibrating and rolling past each other, making and breaking those hydrogen bonds. But water is sticky stuff. It's a relatively small molecule, and yet it has great attraction for itself. So we have liquid water being converted into solid water, which we call ice. So why doesn't a glass of water at room temperature and atmospheric pressure instantly vaporize? Because it's a polar molecule and because there is still an attraction. Even though these molecules are tumbling and sliding past each other, they're attracted to each other by these positive and negative attraction. So if it's a room temperature, let's say 25 degrees C, we're well below the vaporization temperature for water. You'll have some water molecules evaporate and have enough energy to break those bonds and move into a vapor, but the glass of water is going to stay principally a liquid unless you get enough energy into that system to completely break that intermolecular attraction. So the stickier the molecules, the more energy you have to put into that system. The higher the temperature you have to have in order to break those bonds and turn that liquid water into a gas. The same thing's going to be true for a solid that melts into a liquid. The stronger the intermolecular forces, the higher the temperature at which the substance will melt. Okay, so quickly, intra, this is the force that holds atom together. It's not in the force between molecules, it's the force between, let's say, a hydrogen atom and a chlorine atom. We call that a covalent bond. That is not an intermolecular force. That's a force, a very strong force, in between atoms that are within a molecule. So those are the forces that hold atoms in a molecule together. Like oxygen and hydrogen, they have a covalent bond, an intramolecular bond between those two atoms. And those are very, very strong bonds. By at least an order of magnitude stronger than intermolecular forces like hydrogen bonding. So here is a representation of one water molecule. This is a discrete water molecule, and it is being stuck to another water molecule. This is a particularly strong intermolecular force that we call hydrogen bonding. Okay, so you'll want to pay attention to hydrogen bonding. If you've taken biology, you know that hydrogen bonds are the bonds that hold the two strands of the double helix in DNA together. So order of intermolecular bond strength, you have ion dipole. That's when you dissolve an ionic compound and it dissociates in that solvent, and we're going to stick to water for that. So that's the ion dipole force. Hydrogen bonding, which we just talked about, between two very, very polar molecules. There are a very specific set of conditions that are necessary for hydrogen bonding to take place. Dipole-dipole forces exist between polar molecules, and then all molecules, all substances will exhibit what we call London dispersion forces. Doesn't matter what the substance is, if it's got electrons, it's going to exhibit London dispersion forces. And this is the order of intermolecular bond strength: ion dipole, hydrogen bonding, dipole-dipole, and London dispersion forces. London dispersion forces, sometimes just called London forces, sometimes called dispersion forces, or van der Waals forces, are the weakest, but all matter has dispersion forces. Properties of intermolecular forces. All are much weaker than intramolecular forces. Here we have a 10-to-1 ratio. The intermolecular forces require at least 300 kilojoules per mole to break, and then the intermolecular forces between molecules, only about a tenth of that, 30 kilojoules per mole to break those bonds. all are electrostatic interactions. That is, take the positive and negative charges, they attract each other. This would be consistent with an ion dipole force, and this is consistent with two polar molecules, partial positive and a partial negative. Ion dipole forces exist between an ion and the partial charge on an atom or a polar molecule. Water is a polar molecule. You've got a partial negative charge on the oxygen end, partial positive charge on the hydrogens. And so with a sodium cation, what the sodium chloride crystal does is it dissociates into sodium cations and chloride anions in the water, and the water molecules surround them. And the oxygen end, which is partially negative, will surround the sodium cation, and on the other side, the chloride anion, which is negatively charged, will be surrounded by the partial positive charge on the hydrogens. And so what you wind up with is a cage around these two ions. Hydrogen bonding is a very strong dipole-dipole interaction, only between atoms of very high electronegativity, and those are nitrogen, oxygen, and fluorine. Those are the only three, and they have to be covalently bound to hydrogen. It could be oxygen covalently bound to hydrogen. It could be fluorine covalently bound to hydrogen. What this does is it sets up a profoundly strong dipole moment. It's an extremely polar bond. And so you're going to wind up with a positive charge, pretty substantial partial positive on the hydrogen, a pretty substantial partial negative on the oxygen, and the same thing will be true for all of these arrangements. But you need to remember, only nitrogen, oxygen, and fluorine covalently bound to hydrogen can set up an intermolecular force that we call hydrogen bonding. Okay, so water is really good at hydrogen bonding. The negative end of the water molecule oriented to the positive end of the water molecule. So you have this very strong interaction between these two molecules, and keeping in mind the yellow dotted line, that is the hydrogen bond. Okay, that's the hydrogen bond, and many people make the mistake. This is not the hydrogen bond. That's a covalent intramolecular force. This is the intermolecular force between the molecules. So here are the arrangements with three different molecules. You've got hydrogen and fluorine, a very strong covalent bond, very polar, and you have the positive and the negative, and then oxygen with hydrogen in the water molecule. And anytime you see OH in a molecule, you're thinking hydrogen bond. You see OH, and you'll see it all the time in alcohols. You'll see that OH arrangement. You're thinking, oh, that's going to be a hydrogen bonder, and it will be. Okay? And then NH, this is a molecule of ammonia. So here is just another image of a water molecule, of some water molecules that are bound together. You notice that you've got these two non-bonding pairs of electrons on the oxygen, and so water can actually hydrogen bond in 4 different directions, on each of the 2 hydrogens and on each of the 2 non-bonding pairs of electrons that are on oxygen. Makes water, it has a high boiling point, high melting point for such a tiny molecule, 18 grams per mole. Dipole-dipole forces exist between polar molecules. Now, this is chloromethane. That's an image of chloromethane. It's an sp3 hybridized tetrahedral molecule, and it is polar because this atom, chlorine, is more electronegative than the hydrogen is. So all of the electrons are sort of being pulled in toward the carbon and then further pulled toward this electron withdrawing atom, which is the chlorine. And so what you wind up with is a pretty darn good positive charge on the hydrogen end and a pretty darn good partial negative on the chlorine end. Now, this is not a hydrogen bonder. It's just a polar molecule, and polar molecules exhibit what we call dipole-dipole forces. This is a type, hydrogen bonding is a type of dipole-dipole force, but it's a super strong dipole-dipole force. Whereas with the chloromethane, this molecule here, it is a polar molecule, it is a dipole-dipole force, but it's relatively weak when compared to the strong dipole-dipole force in hydrogen bonding. So effects of hydrogen bonding in water accounts for the high boiling point. The high surface tension of water accounts for the high viscosity of water. Viscosity means resistance to flow. So they're just resisting flowing past each other.